So continuing with air quality models. So continuing with air quality models, we left off where the next step we need to look at is the plume rise. So what we will start with today is looking at plume rise. So looking back at the images that I showed you during the meteorology lecture, we have two mornings, one in February, the other in March in 2015. And what you see is actually very different temperatures. So much colder and calm, so very little wind. And you see, as we talked about, this plume rise, and then you see a horizontal movement. On the other hand, on March 2nd, you see a higher temperature, much higher wind speed, and you see very little plume rise. So in order to be able to predict the concentration downwind and to predict the transport of these pollutants, we need to be able to predict the plume rise. Now, the plume rise will denote as delta H. And as you saw in that previous, those previous photos, as the plume moves away from the stack, what happens is it loses vertical momentum fairly quickly due to drag and entrainment of the surrounding air. And that causes the plume to bend in the direction of the wind. But in many cases, it still rises. And that rise is due to a number of factors. One is buoyancy. The density of the stack gas is often less than the density of the surrounding air. So it's less dense, it tends to be more buoyant. The stack gas has velocity, so it has a momentum term, and that momentum helps to carry that wind, that stack gas, in a vertical direction. The other thing, that stability of the atmosphere will play a significant role on the plume rise. Typically what we see is low wind velocity will have a plume that will rise higher. If there is high wind, then you'll see less vertical motion. And that's exactly what you see in those plumes, which really are plumes of water vapor. So I want to make sure you realize that for the most part, what you're really seeing is the plume due to water vapor. Other things that will play a role, the molecular weight of the gases. That's important. Both the ambient temperature and the stack temperature will play a role, as will the exit velocity. And we will take all of these into account in predicting plume rise. Now, we're balancing the height of the plume with, we want it high enough that the concentration at ground level is less than the criteria. At the same time, we don't want it too tall. It's too tall, that increases cost significantly. But as we mentioned, that tends to transfer the problem downwind. So the equations we have for plume rise vary with conditions. So for stability class E and F, we'll use this set of equations. So we have two factors we have a buoyancy parameter, F, and we have a stability parameter, S. Note here the units are extremely important. Your gravitational acceleration is 9.8 meters per second squared. The radius of the stack, that's the inside radius, is in meters. Stack gas exit velocity is meters per second, and your temperatures need to be in Kelvin. For the stability parameter, your environmental lapse rate, which is what this is, needs to be in degrees Celsius per meter. And note, this corresponds to the dry adiabatic lapse rate. So be careful with these units. They are critical in determining the stability and the buoyancy parameters. Now, if your stability class is A through D, then you'll use this set of equations. So here, again, you actually have two different equations. We'll use the same buoyancy flux that we just determined, but what's different is the equation for the plume height, and it will vary depending on the distance downwind. So x of f is the distance downwind to the point of the final plume rise. So if we go back here, you can see pretty much the distance of the final plume rise is almost zero. It's essentially at the stack. Here, that plume is still rising at some distance from the stack itself. So if you're at a distance greater than the distance to the point of plume rise, then you will use this value x of f. If you are less than, the distance is less than that x of f, then you'll simply just use the distance of x. And you can see here that we have two different equations for x of f, depending on that buoyancy parameter. All of these equations are empirical, which is why it is extremely important that you use the proper units in these equations. So let's look at an example here. So we have a large power plant. It has a stack that is 250 meters high. It has an inside radius of 2 meters. The exit velocity of the stack gas is 15 meters per second. The temperature of the stack gas is 140 degrees C or 413 degrees Kelvin. The ambient temperature is 25 degrees. Wind at the stack height has a velocity of 5 meters per second. And you're asked to determine the effective height of the stack, one, if the temperature is stable, with a temperature increasing at a rate of 2 degrees C per kilometer, and if the atmosphere is slightly unstable at class C. And I should have added, okay, so let's look at the parameters that we have. So we have H is equal to 250 meters. So that's the height of our stack. The inside radius is 2 meters. The exit velocity is 15 meters per second. The temperature of the stacked gas is 413 Kelvin. The ambient temperature is 298 Kelvin. The wind speed at the height of the stack is 5 meters per second. And delta T over delta Z is 2 degrees C per kilometer, or 2 degrees C per 1,000 meters. So for stable conditions, the stability parameter is equal to G over T sub A delta T over delta Z plus 0.01 degrees C, and that is equal to 9.8 meters per second squared divided by the ambient temperature times 0.001, and notice our temperature is increasing, plus 0.01, and that is equal to 0.0004 inverse seconds. F, our buoyancy parameter, is equal to G R squared V sub S 1 minus T sub A over T sub S. So we substitute in, that's 9.8 meters per second squared times 2 meters squared times 15 meters per second times 1 minus 298 over 413, and that is equal to 164 meters to the fourth seconds cubed. That's the units. So that's our buoyancy parameter. So delta H is equal to 2.6 times F U sub H S over 1/3. Now, in actuality, we really should be using the wind speed at the effective stack height. We don't have that, so typically what is done is to use the wind speed at the stack height. And this is 2.6 times 164 over 5 meters per second times 0.004. And this is meters per second. And this is meters fourth second cubed. And this is to the 1/3. And this is equal to 113 meters. So that's delta H. So the effective height is equal to the stack height plus delta H, and that is equal to 250 meters plus 113 meters, or 363 meters. So under that stable condition that you have been given, the stack height, sorry, this is kilometers. The stack height is 363 meters. Now, for the unstable condition, so we have class C, we had F is calculated the same way. So F is still 164 meters to the fourth second cubed, and that is greater than 55 meters to the fourth second cubed. So therefore, we'll use the equation X sub F is equal to 120 F to the 0.4, and that is 120 times 164 to the 0.4, which is 923 meters. Delta H that these conditions are equal to 1.6 f to the 1/3 x sub f to the 2/3 over u sub h. So we're calculating the plume rise at the point where the plume no longer continues to rise. And that is equal to 1.6 times 164 to the 1/3 times 923 to the 2/3 over 5 meters per second, and that is 166 meters. And here h is equal to the stack height plus the plume rise, so that's 250 plus 166 meters, or 413 meters. So in this case, under the unstable condition, you see that for identical wind speeds, you see that the plume rise is greater than it would be for the stable conditions. The caveat here is that the wind speed is the same. So this gives you both a way to calculate the plume rise, which we'll need in order to be able to determine the transport. So in the previous problems that we did on Wednesday, I gave you the plume rise. For a number of the homework problems, you will have to calculate the plume rise and then calculate the concentration. Now, the other situation we can encounter is where we have a temperature inversion. Now, where we have a temperature inversion, we'll use the term L to describe that mixing height. So we've talked about mixing height. Now, we talked about how that when we do this modeling, when we're looking at ground level concentrations, we develop the equations assuming that we have a reflection of the plume as it hits the ground surface. We will, in this case, assume that we have a similar reflection when that plume hits the mixing layer. So let's look at this with highlighter. So here's our plume. It hits the ground layer, and we have a reflection backwards, upwards. The plume at this point here hits the mixing layer, and we will assume we have a reflection back down towards the ground surface. So we have a situation here where we'll describe X sub L as the point where that plume hits the mixing layer and begins to reflect back downward. We have a point here that we will refer to as 2 times that X sub L distance. And what we will assume here is that we have complete mixing. So in this region here, we have complete mixing, and the concentration is no longer a function of Z. So the concentration will change in the X direction, but it doesn't, and it changes but it won't change in the Z direction. So think about it as we have complete mixing in the Z direction. The equation that we can, or the way we determine the distance X sub L is using this equation here. So we have the dispersion coefficient in the Z direction. That is equal to 0.45 times the difference between L and the effective stack height. And again, this is an empirical equation based on the modeling efforts that have been done. At for x greater than or equal to 2 times this x sub L, we can use this equation here. If we are at the center line, then this term here equals 1. Y is equal to 0. And this term here becomes 1. So then it's only this part of the equation that we need to worry about. So again, in this case, we're looking at Q is our source term. U sub H is the wind speed at the effective stack height. We have a dispersion coefficient in the y direction, and L is the elevation of your inversion layer or your mixing height. Any questions about this so far? So if your distance is less than x sub L, so let's go back and look at this diagram here. If you are in this region here, you'll use the standard Gaussian dispersion equation. If you are in this region here, in this region, then you will interpolate between the value at this point and the value at 2 times x sub L. So there is no good modeling equation to describe the pollutant concentration in this region right here. So we just simply interpolate. If you are at distances at or greater than x sub L, then you will use this equation here. And again, if you're at the center line, this term becomes 1, and you only need to use this part of the equation. So let's look at an example here. We have a stack, and you're given the effective stack height in this case. It's emitting SO2 at a rate of 2 times 10 to the 8 micrograms per second. We've got a wind speed at 10 meters of 2.5 meters per second. It is a clear night with an inversion layer at 300 meters, and you're asked to estimate the ground level SO2 concentration at a distance directly downwind, so y equals 0, at a distance that is 2 times x sub L, 2 times that point where the reflection begins to occur. So the first thing we need to do is determine the stability class. We're told it is a clear night. The wind speed is 2.5 meters per second. So we are at a stability class of F. The next thing we need to do is to determine the wind speed at the effective stack height. So we use the equation U sub H is equal to U sub A, Z H over Z A to P. We have stability class F, it's stable condition. So we have P is equal to 0.6. We'll assume that we have rough terrain. So this is equal to 2.5 meters per second times 100 divided by 10 to the 0.6, and that is equal to 9.95 meters per second. So we have now U at the effective stack height. We need to determine X sub L. So at X equals X sub L, then the dispersion coefficient in the Z direction is equal to 0.47 times L minus H. So that is equal to 0.47. L is 300 meters, the height of the inversion layer, minus the effective stack height, and that is equal to 94 meters. So this is the dispersion coefficient in the Z direction. We need the distance, though. And the way we can do that is to use, we can initially estimate it with the graph. So we're at a point, Z is equal to 94, right in here. We'll read down, and that tells us that the Z is approximately 10 to the 5th meters. So that gives us an approximate value. We can determine a more accurate value using the equations that are given. So we have the dispersion coefficient is equal to 94 meters. And that is equal to, this is X is definitely greater than a kilometer. That's equal to this equation here with the values for C, D, and F. So that is equal to 62.6 X to the 0.180 minus 48.6. And if I solve then for X, that is equal to 97 kilometers, or 9.7 times 10 to the 4 meters. I apologize for all the extra lines. This then is X sub L, because we defined it as such. So then now we need to find the dispersion coefficient in the Y direction, and that is equal to A times X to the 0.894. So that's this equation right here. And A is equal to 34. X we've just determined, it's 97, but remember, we're actually determining this for 2 times X sub L. So what we have, so we'll multiply this by 2, 0.894, and that is equal to 3,771 meters. From a physical perspective, what does that mean? With a dispersion coefficient that large, what is it telling us?
Does it mean that the concentration along like the along the y-axis is like very dispersed?
Exactly. It's extremely dispersed or in the y direction, which therefore means that a large population is affected. So the smaller that dispersion coefficient, think of it as the sharper the curve, the more concentrated your pollutant is. So the more dispersed it is, the greater the population you're affecting under these conditions. And that's why these stable conditions are so hazardous because concentrations may be slightly lower, but they're affecting a very large population. So C sub x, and we're looking at 2 times x sub L, and that is equal to Q over 2 pi to the 1/2 U sub H, the dispersion coefficient in the y direction, times L, and that is equal to 2 times 10 to the 8 grams per second divided by 2 pi to the 1/2 times 9.95 meters per second times 300,771 meters times 300 meters, and that is equal to 7.1 this should be micrograms per meter cubed. So that is the concentration to which this whole population is exposed. Just to compare this, the 1 hour SO2 limit standard is 75 parts per billion, and that is 200 micrograms per meter cubed at 1 atmosphere, 25 degrees C. So that just gives you a comparison. Concentration is much less than that, but you have a large population that's exposed. Any questions about these units or these problems? One of the things I want to mention, have any questions? Feel free to let me know or write it in the chat. Just to reiterate, this is extremely important in your homework. Q has units of mass per time. And so typically it will be in kilograms per second, grams per second. In this case, it's in micrograms per second, but it's mass per time. Q sub S is equal to Q divided by the surface area. So think of that as for instance, if we're looking at a box model, that's the area over which the pollutant is being dispersed. So it's your ground, I think it's really your ground, the area at the ground level. It's not the area across that plane where wind is moving into the box. It's at the ground level. So make sure, be careful with these units. Uppercase Q is O in any of the equations is mass per time. Lowercase q sub s is a specific mass rate, and it's your Q divided by the surface area. The last part of the model, or the last model that we'll look at, is a line source dispersion model. It's essentially the same concept that we've been using, but this is used where we have what is a line source. So if, for instance, we're concerned about a population that is living along a highway, and we want to know what concentration of pollution carbon monoxide, for instance, they're exposed to on a daily basis based on the number of vehicles moving along this highway. We can also look at it in terms of agricultural burning along the edge of the field. So basically, while the field itself is an area source, we can model it by, this is our area of the fire, the wind is in this direction. We can essentially model that plume as a line source. We can do the same thing, line of industrial sources on the banks of a river. Together, because we have multiple sources, we can describe that mathematically as a line. If that is the case, then we can use this equation here. So think of this as here's our road, and the cars are moving along the road. The wind, I'll just do it this way, is in this direction here. So the wind is perpendicular to the road, and we have some homes over here, and we're worried about the exposure of these people to, let's say, carbon monoxide. In this case, Q is a rate per time divided by the distance perpendicular to the wind direction. So it has units of mass per length per time. So this Q here has different units than Q sub S, different units than Q. Dispersion coefficient is the same. This wind speed, we're often looking at this at ground level, so we will simply use U sub A. So we have a situation here where we have the federal emission rate for carbon monoxide is 3.4 grams per mile driven. Assume that the highway has, counting vehicles, we have 10 vehicles per second passing a given spot, each emitting carbon monoxide at the federal emission level. The wind is perpendicular to the highway and is blowing at a rate of 5 miles per hour or 2.2 meters per second. It's an overcast day, and we're asked to estimate the ground level carbon monoxide concentration 100 meters from the highway. Overcast day at this wind speed would be a stability class D. So let's go back to that same table that we just used in order to determine the stability class. Thought I did this. We'll add a new slide in here. So Q is equal to 10 vehicles passing per second. We have 3.4 grams of carbon monoxide emitted per vehicle per mile. And there are 1,609 meters per mile. So that is equal to 0.021 grams per second meter. The dispersion coefficient in the Z direction for stability class D is equal to 33.2. The distance X, we said, was 100 meters or 0.1 kilometers. This is in kilometers. 0.1 times 0.725 minus 1.7, and that equals 4.6 meters. Okay. I'm just going to write this below it. Just make sure you can read it. Okay. And then C is equal to 0.1 kilometer. And that is equal to 2Q over the square root of 2 pi times the dispersion coefficient in the z direction times u. That is equal to 2 times 0.02 grams per second meter. I'm going to convert to milligrams and divide that by the square root of 2 pi times 4.6 meters times 2.2 meters per second, and that equals 1.7 milligrams per cubic meter. And just for comparison, the 8-hour carbon monoxide standard is 10 milligrams per meter cubed. So assuming that the homes are 100 meters away from the highway, the concentration here is much less than the standard. So we can at least state that that population is exposed to a carbon monoxide level, the 8-hour standard, that is less than the ambient, the NAC level for carbon monoxide. So that gives you some idea of some of the models that we can use or how we can use these dispersion models. This is just a summary of the various different models. So in this case, we have a concentration in the X, Y, and Z directions. Here, Z is equal to 0, so this is a ground level concentration. Here, Y is equal to 0, so we're along the center line. And we have a situation here where the source is at the ground level. So think of this as the campfire. So you've got a source, a point source at the ground level. So hopefully this helps in terms of performing calculations regarding the transport of pollutants. And we've got a few minutes. Happy to stay also after if anyone has any questions.